All right. Hello and welcome everyone. I hope I am audible to all of you.
Yeah, yes, sir.
All right. So let me just share my screen. All right. So we want to know more about Apache Spark today. All right. So our discussion today will be on. All right. Now, before we jump into what is Apache Spark, why is it used? So in very simple terms, it's a data processing engine. All right. This is a framework that lets you process huge amounts of data. All right. This is a unified computing engine. All right. With a set of libraries which can help you process data in parallel on a cluster of compute. Right. Very simple definition. This is the definition that you'll see everywhere. All right. And it is the most actively developed open source engine, right, to perform data processing. And it's a very standard tool for the developer or data scientist, right, who are interested in big data. So wherever you see data analysis, big data, data processing, you will always hear this word Apache Spark, like because it supports multiple used programming languages like Python, Java, Scala, R. We'll see what they are, right? And it includes a lot of libraries for diverse tasks ranging from SQL to streaming and machine learning as well. Now, before we jump into what is Apache Spark, right? Let us try to understand why Apache Spark came into the picture. All right. So before Apache Spark, we had the Hadoop system. Hadoop was used to process data before Apache Spark became popular. All right. Now, Hadoop is also an open source framework. It is designed to store and process large amounts of data. All right. And even in Hadoop, we had something called as a distributed computing. All right. Or the data was processed over a cluster of compute. Now, cluster, all of you understand, it's like a collection of multiple machines. I'm not processing my data on a single machine. I'm processing my data on multiple machines. Now, why that was done, we'll come to that. So Hadoop is where you will have multiple computers, multiple nodes as we call it, right? A cluster on which your data is being processed. Hadoop contained two main parts. All right. One was something called as HDFS or Hadoop Distributed File System. All right. This was a file system which was used to store data. All right. So this was a file system used by Hadoop to store data, where the data was actually divided into smaller parts. All right. So you will get the main data, you'll get the whole data, and then you will start dividing into smaller chunks, and you would distribute these smaller chunks across multiple machines in the computer. All right. So this became one, two, three, four. So you divided your entire data into four parts, four smaller parts, and then you would put that smaller parts into the cluster. All right. You will send one part or one chunk to one node. All right. And then the data was processed in parallel and then finally brought together. The second main part was the map reduce uh, model. All right. So MapReduce was the programming model that was used to process the data which was stored in HDFS. All right. So Hadoop was storing data in the HDFS and then processing it using the MapReduce function. All right. Where this can be divided into two parts. One was map function and the other one was reduce function. The map function would break down the data into smaller parts and process them in parallel. All right. So this was your data, which was broken down into smaller parts and then processed on a cluster of compute in parallel. So that was done by the map function. And the reduce function would take individual results from all of these clusters, nodes in the cluster, and put your data back together. All right. So it will combine the results from the map phase and put it into a final output. So Hadoop was handling large scale data processing across many computer, uh, or as we call it node. All right. I can either call these as computers or I can call them as nodes. Right. Now, uh, the system was again fault tolerant. Fault tolerant basically means that it was ready for any sort of faults. Fault could be any system outage or anything. All right, so the system was fault tolerant because the data was replicated in the HDFS. All right, even if let's say uh, data was being processed on this first machine and for some reason this machine goes down, so it will keep a record, all right, of the data that was being processed on this machine. All right, your data is not lost. It will try to process that data again, right? And this was open source, it was scalable. But again, there were several limitations with this model, right? So let's try to see what the limitations were, which led to the development of Apache Spark. So the very first limitation was that Hadoop used to process data very slowly. All right. The MapReduce framework, it used to process data in batch modes, first of all, and the intermediate results of this processing. So whenever you're processing data, right, you will have some intermediate results there. Now, this intermediate result was, uh, was written to a disk. All right. So there was a reliability, all right, or there was a reliance on disk input output. All right. Now, when you are reading data from the disk and writing data from the disk in middle of your processing, that will act like a bottleneck for the entire process. All right. So that made the entire process very slow. All right. For iterative tasks like, where you were having real-time data analysis or you were doing machine learning. So since Hadoop was reading and writing data from the disk, that made the entire process really slow. All right. Secondly, there was very high latency. All right. So Hadoop is not suitable for low latency or real-time applications. All right, because it is designed for batch processing. It was unable to process the real-time data. Real-time data, as we call it, is when the data is arriving instantly and you want to process it as and when the data arrives. All right. Then there was a rigid programming model. All right. So the map reduce programming model. It's a very complex model, and it requires developers to write a lot of code. All right. Even for very simple tasks, you have to write a lot of code to work with the MapReduce function. All right. And then obviously there was lack of versatility. Uh, Hadoop was mainly focusing on batch processing, and it does not have a built-in support for the workloads like real-time streaming or interactive queries, writing interactive queries, or with machine learning tasks. All right. And it doesn't utilize the resources efficiently. All right. So there was a limitation on the performance as well. All right. It's heavily dependent on disk-based operation. And this was the major problems with the Hadoop system. All right. Just give me 1 minute. I'll try to rejoin because I am hearing my own voice. So just give me a second. I think I need to change the audio connection. So just put in a timer and I'll be back. Just wait for 2 minutes. I'll change my audio system. The All right. Am I audible now clearly?
Yes.
Yeah. Yeah.
Yes.
All right. All right. So when you start working with data, right now, the point comes as to why you should learn Apache Spark, right? So when you start working with data, all right, you primarily use cloud-based services like Azure Synapse Analytics, or you use Azure Data Lake to store this data. You have Azure Stream Analytics to deal with the streaming data. However, you will quickly realize, right, that understanding Spark, all right, not just limited to the cloud environment, but beyond cloud environment was very essential, all right, for your growth as a data engineer. And that is why we have this session on Apache Spark, and we'll walk you through the entire process of how you're going to use it. Now, what makes Apache Spark unique is that it deals with all of these problems, all right? It gives you something called as in-memory processing. Now, what does this mean? That when you're using Apache Spark to process your data, compared to Hadoop, it uses something called as in-memory processing, right? So unlike Hadoop, Spark is going to process the data in the memory itself whenever possible. So it will use RAM, it will put the intermediate data in the RAM and process it in the RAM itself. All right, and it significantly reduces the disk input output that makes the entire process in certain cases, it's 100 times faster. All right, for a certain workload, the process becomes 100 times faster. That is what Apache Spark claims. All right, especially processes where you have to, iterate again and again and again, like machine learning, right? Then Spark was also able to support real-time and batch processing.
Can I ask a question here?
Yeah, yeah.
Like if it is in memory processing, in real time, generally deal with the terabytes of data. When we are dealing with 5 terabytes of data,
Mhm.
5 terabytes of memory will not be available. Then
Yes.
Spark, how it will process?
All right. So I'll answer your question in a very short way currently because that is something that we were just going to. Now, within the Spark architecture, you have a driver program, correct?
Yes.
There is a driver. This driver program is going to break down your data. Let's say it's 1 terabyte of data. It is going to break this 1 terabyte of data into, let's say, 10 pieces, 20 pieces, whatever the amount is. Let's say the each chunk is of size 2 GB, right? For example, or let's say each chunk came to be 5 GBs.
So it will be in HDFS, right? The data will be stored in the HDFS in this case. All this 1 terabyte of data initially driver program will be in the HDFS.
See,
From
when
there,
you're talking about Hadoop specifically, then yes. If you're talking about Spark, then it could be stored in HDFS or it could be stored in other locations also, other cloud locations also. Spark integrates with Amazon S3, Azure Data Lake. It can also work on top of HDFS.
so depending on the storage, again, the splits will happen, right? If it is HDFS, the block size is 256 MB. So depending on the data size, it will divide the storage.
Yes, see, how and what size it will divide the storage, that will come to later. But I think the main question was if the data size is more than the size of the memory, right?
Yes,
What is
correct.
going to
Yeah,
happen, right?
yeah,
So let's
correct.
say it's a 5 GB chunk that is getting created. Now, how does this work is you will have a lot of worker nodes. Yes, let's say for this example, we have three worker nodes. Now, each has, let's say, a RAM of 8 GB. All right, that means that in one go, all of these machines can process 5 GBs of data. Yes or no? So what driver program will do? It will take the entire chunk of data and the driver program is responsible. Driver program is solely responsible to uh, orchestrate this entire processing or manage this entire processing. In middle, you have something called as a cluster manager. All right. This cluster manager will be connected to each and every node in the cluster. And this cluster manager is also what the driver program will be connected to. All right. The cluster manager will keep an eye on each of these nodes. It will try to see which node is now idle, which node is busy, and that information it will keep on giving to the driver node. All right. That I have one machine available, give me more data. So whatever code that you want to process, right? Because when you're processing data, right, you will have certain code that you want to use to process that data, right? And we know that in Spark, you can use many programming languages to transform your data, process your data, such as Python. You can use PySpark, you can use SQL, you can use R, you can use Java, you can use Scala. So a lot of programming languages are there that you can use to interact or transform your data over here in Spark. Now what happens is driver will send 5 GBs to each of these nodes, right? The cluster manager will keep an eye as to which node becomes idle. Let's say this node N1, oh sorry, N1, I'll call this N2, N3. Let's say N1 processes the data first and it is empty now. It has processed this 5 GB of data and whatever the output size is, it keeps it. So cluster manager will let the driver know that we have another space available, send more data. Driver will send another batch of 5 GB data, all right, which will now go to N1. Similarly, N2 completes, the output will be stored here, right, collected, and new data will arrive here. So if you have, let's say, chunks of data like this, then one by one, each chunk will go to the nodes. Is that clear? One by one, the driver program will send each chunk to the node based on the information that is it is receiving from the cluster manager.
Yeah, thank you.
All right. Now, Spark also gave you the support for real-time processing of data. All right. Hadoop was limited to batch processing, whereas Spark supports both batch and real-time processing. All right. So there is a functionality called Spark streaming. All right, which makes it suitable for diverse workloads. Now, this was a unified framework, so it was very versatile. All right, Spark provided libraries for different tasks. It had something called as Spark SQL. All right, that would um, help you deal or manage structured data and write queries for structured data. You had MLlib for machine learning. You have GraphX for graph processing. You have Spark streaming for streaming data. So various libraries were available within Spark to deal with multiple types of data. All right. Spark was again very simple to use compared to Hadoop. All right. Compared to Hadoop, it was very simple and it had more flexible APIs. All right. It offers high level APIs. Right, Spark offers these high-level APIs in multiple programming languages, as we discussed. You will get these APIs. These APIs will let you interact with Spark, all right, and write your program that is going to process the data. Now, this program to process the data could be written in Python, Scala, Java, and R. So this opened the gate for a lot of developers, right? I could be a good Java developer. I might not be really good in Python, or I might be a good Python developer who has no idea about Java. Somebody would know R, somebody would know Scala, right? So like this, a lot of developers were now able to work with the Spark architecture. So this reduced the entire development time, right, and the complexity as well, if you compare it to the Hadoop's MapReduce function. And Spark was also utilizing the resources efficiently. Right, it optimizes the resource utilization. It leverages distributed memory, right, which is there across the cluster, and it allows for better performance compared to the Hadoop's disk reliant approach, right? Because Spark is relying on memory, so it is able to do the task in a much faster or much less time. All right. So this is what Spark gave you above the existing Hadoop. Now, when we use or when we talk about Spark, right, the standard definition of Spark is, as I said, it's a unified computing engine, all right, with a set of libraries for big data, right? Unified compute engine with a set of libraries to process big data. So these are the three important terms, right? We need to understand what is the word unified meaning here, what is the compute engine, and what are the libraries that we are talking about, right? So the key goal that Spark's key goal or the key offering, I would say, is a unified platform for writing big data application. All right. So what do you mean by unified? Unified means that Spark is designed to support a wide range of analytics tasks. All right. Ranging from, let's say, simple data loading and writing SQL queries to machine learning and streaming computation. So everything was possible, right, within the same platform. All right, over the same computing engine with the consistent set of APIs that you had to interact with Spark, right? The main reason I would say, or the insight behind this goal, right, is that it in your real world data analytics tasks, right, whether they are interactive analytics, all right, in a tool such as your Jupyter notebook, or it's a traditional software development for production application, they tend to combine many different processing types and libraries together, all right, and this unified nature, it makes these tasks both easier and efficient to write, all right. uh, then you have the compute engine. Uh, at the same time, where Spark is, unifying the entire or strives for unification, all right, it also carefully limits the scope to a computing engine, all right. What do we mean by limiting its scope to a computing engine? So this means that Spark is going to handle, all right, uh, loading data from storage systems, multiple storage systems, performing the computations on it, right? Uh, uh, just a minute. Yeah, sorry. Yeah. So you can use Spark with a variety of persistent storage systems. You can include that includes, cloud storage systems such as your Azure storage or Amazon S3, or a distributed file system such as your Apache's Hadoop, right? So you can also use key value stores such as Apache Cassandra, right? You can use message buses such as Apache Kafka. However, Spark neither stores data long term itself, all right, nor it favors one over another, all right. The key motivation which is present here is is that most data already resides in a mix of storage system, all right. Data is very expensive to move, right? So Spark focuses on performing computation over the data, no matter where it resides, all right. Now, it was again launched in 2009, all right. There was a Spark research project, and it was published in the paper which was titled Spark, the cluster computing with working sets, in around 2009, all right. So at that time, Hadoop's MapReduce was the dominant parallel processing engine for clusters. So now, when you come to Spark, right, the basic architecture you want to understand. All right. So when you think of the word computer, all right, you think about one machine sitting on your desk, right? One machine like this sitting on your desk at home or at work. And this machine, it works perfectly for your day-to-day tasks, right? You can be watching movies, you can be working with a spreadsheet software, right? However, many users, right, uh, at some point they have an experience. All right, there are certain things that your computer is not powerful to perform. All right, your computer is not powerful enough to perform those tasks. All right, and one particular challenging area is data processing. All right, now single machines, they do not have enough power, enough resources, right, to perform computation on huge amounts of information, right, your big data. And that is where we move from a single machine to a cluster. Earlier, what people would do is they had a machine, they were trying to process the data, but somehow the resources were pretty less, right? The data processing would not happen as efficiently as they would have, imagined. So what they did vertical scaling. They did vertical scaling of this existing system. Now, what vertical scaling means? It means increasing the capacity of individual machines. That is vertical scaling. All of you know what scaling means, right? Adding more resources, adding more machines. So vertical scaling means that you pick up an existing machine and you resize it, all right? And you make it a bigger machine. How? If the RAM here was 8 GB, you would increase the RAM to, let's say, 64 GB here, right? But vertical scaling has had its own limitation. You could only resize a system to a specific point. After that, it would not make any sense. All right. It was not viable to increase the size again and again and again multiple times. So there is a limit that you would reach here and you would not be able to go beyond that. And that is where these developers realized that instead of vertical scaling, all right, which basically increases the capacity of an existing resource, we should go for horizontal scaling. What is horizontal scaling? Vertical scaling means increasing the capacity. Horizontal scaling means increase the number of resources. All right, so instead of increasing the capacity of a single machine here, I would introduce more and more machines which will be used to process my data, right? All of these machines are called as nodes, all right? All of these machines are your nodes. Sometimes we also call them, not sometimes, we will come to that definition later on. But all of these machines are your nodes. Let's say each machine has 20 cores of CPU, and let's say um, some 100 GB RAM. Let's say these machines have 100 GB RAM. So when you combine this, right, because you have 5 machines here, right? So you'll have 100 cores of CPU, right? 500 GB RAM. This is the total compute that you have available over here. Now, all of these nodes will together form a cluster. Just a second. All right. They form something known as a cluster. Now, this cluster is a group of computers, all right, which are going to pool their resources together. All right. They will pool the resources of all of these machines together. And that gives us the ability to use all the cumulative resources, all of these resources together all right, as if they were a single computer. All right. Now, a group of machine alone is not powerful, right? You need a framework that is going to coordinate the work across these machines, correct? If you have multiple machines, and you don't have any idea how to coordinate your tasks on these machines, right? So what you are going to do, right? So that is why the processing machines, they became the worker nodes. We call them worker nodes. All right. These became the worker node, whereas you will have another machine, all right, over here, that is going to orchestrate the entire data processing. It is going to manage, the data, the code that you're going to write, right? All of this will be managed over here in the driver node. All right. Now, driver node or the driver process, as we call it, uh, and the worker node or the executor node. We call them worker also, we call them executor also. Sometimes you will hear the word master slave relationship. So this will be called as a master, this will be as a slave, or like this will be as a master, these will work as the servants, right? Where the masters are going to give instructions to the servants. So driver node or the driver process will run your main function. All right. And it will sit on one node on the cluster. All right. This machine will also be a part of the cluster, but this will be a driver node. All right. So inside the cluster, you will have one driver node and the rest will be the worker node or the executor nodes. Now, the driver node will be responsible for three things, three main components. All right. One, it will maintain all the information about the Spark application. All right. It will respond to the user's program or the input. All right. It will analyze, distribute, schedule the work across the executors. The driver node will be responsible to break down the data, distribute it, and schedule the work across these executors. All right. And the driver process is absolutely essential. It is the heart of the Spark application. All right. It will maintain all the relevant information during the lifetime of the applications. Whereas these executors are responsible for actually carrying out the work. All right. They perform the task that the driver is going to assign to them. All right. So that means that each executor is only responsible for two things. One, executing the code which is assigned to it by the driver. All right, whatever the driver has asked the executors to do, they will process that code on the data that has been given by the driver. All right, and then report back to the driver. All right, first they will receive data and the code from driver to process it. Then they will report back to the driver the state of the computation. All right, whether they were successfully able to do it or not. So this is your driver, right? The driver will contain the data. The driver will also contain the user code, whatever code you want to run on this data, right? And then you will have something called as a cluster manager. And this cluster manager will interact with all of these nodes. All right. There are various cluster managers. Spark will have its own cluster manager also, or you can use another cluster manager such as Kubernetes. Now, we all know that Kubernetes is used to manage the cluster, right? You have Yarn, you have Mesos. We'll talk about them later. All right. Now, the cluster manager will control the physical machines. All right. And it will allocate the resources to the Spark application. The Spark application will be running here, and it will receive information from the cluster manager regarding the availability of resources. All right. The moment a node becomes empty, the moment the node has finished processing the data, the cluster manager will report to the Spark application running on the driver node that we have an empty node. Please send more data. All right. So cluster manager keeps the track of all the resources which are available, and the driver process is responsible for executing the driver programs, commands across the executors to complete a given task. All right. And the executors, for the most part, will always be running the Spark code. All right. And the driver here, all right, can be, I would say, driven. The driver could be driven using various programming languages. All right. Such as your PySpark, Scala, Java. So you can do that. Now we have something called as Spark's language APIs. All right. So Spark's language API will make it possible for you to run the Spark code using various programming languages. All right. There are certain core concepts within Spark. All right. In every language, and these concepts are then translated into the Spark code. All right. That basically runs on these machines. All right. On the cluster of the machines that you have. If you just use the structured APIs that lets you deal with the Spark application, all right, or that lets you run the Spark application, right? You can expect all languages to have a similar performance characteristics. All right. You have Scala, Java, and they will provide almost similar characteristics because with the language, you are just trying to interact with Spark. The actual processing will be done by the Spark engine itself, right? So it does not matter in which language you have given the instruction. When the processing starts, all right, that is where the Spark engine will come into the play. The language APIs are only used to give instruction to the Spark application. All right. So Spark is primarily written in Scala. All right. So Scala is like the default language for Spark, right? You have Java, even though Spark is written on Java, right? But Spark's author have also very carefully ensured, all right, that you can write Spark code in Java as well, right? Then Python, we all know Python supports nearly all constructs that Scala supports. We have various APIs in Python that exist that can be used. You have SQL. Spark supports, SQL as well. It lets you deal with the structured data with SQL-like queries, and it has two commonly used R libraries as well. All right, you have Spark R, and then you have one second, Spark LYR, right? So two are there. Now, I think we have So we'll keep it limited to this. All right, the demonstration on the basic of Spark architecture. When we move forward, we'll take a deeper look into the driver program, what it can do, what all it can do. There is an opportunity as well for us to understand different various cluster managers, how they work, right? To understand the Spark context, which is essential object in the Spark, right? So eventually you need to first of all understand how is Spark functioning? What are the tasks? What are the jobs? What are the stages in Spark? All right. So a job in Spark is like a sequence of transformations and actions that you apply to a given data set. All right. So when you perform an operation like, let's say, filtering of data, mapping of data, aggregating data, Spark is going to convert all of these individual operations into multiple tasks. All right. And each task will act like a unit of work that will get executed on an executor. All right. So the overall operation is the job. The job is broken down into smaller tasks which are independently executed on the executor. All right. And the first thing that happens when you start processing your data is job submission. The first step is called as job submission. Then the second step is data partition. All right. Then once the data has been divided, you will have task distribution. All right. The driver will send the partition along with the code, whatever the smaller chunks of data that it has created, along with the code that has to be, that will be processing the data which is being sent. That task will be distributed by the driver to the executors. Then parallel execution will start. All right. So executor will now run tasks in parallel. All right. Applying all the transformation that has been, provided with the code. All right. One executor will process, let's say, row number 1 to 5,000. The other one will process row number 5,001 to 10,000. Then another executor will process 10,001 to 15,000. Right. Now, there is something called as data shuffling also, but this is not mandatory. This is just, you know, it's if needed, right? It's optional. If your job that you're running, it requires data from different partitions, right, to be combined together. Let's say you want to run a group by operation, all right? So in that case, Spark will perform something called as a shuffle, and the shuffle process will redistribute the data across different partitions, all right, which can be very resource intensive, but it is necessary for your accurate results. And then finally, you will collect the results together, combine them together. Each executor will produce an output, and each of this output is sent back to the driver program. The driver will collect all these outputs from various executors, right? Coming from various executors, and it will combine them if it is necessary, right? And it writes the final result once it has received the output from various all the executors, right? It could be just a single output or could be multiple outputs coming from a single executor. It will combine all of that together and it will put it to the data store wherever you have to put your data back. All right. So the final result is combined and put back into the target data store that you have. All right. So if you want to understand whatever we've done today through an analogy, right? So imagine that you're organizing a huge event, right? Let's say it's a music festival. And in that music festival, you need to coordinate between multiple teams. All right. There would be multiple teams. Somebody would be managing the food stalls. Somebody would be, let's say, managing the stage, building the stage, right? Somebody, one team would be, not somebody, but a team. So team would be managing the food stalls, a team would be managing the stage, one team would be managing all the tickets. There would be a security team. Sorry. So all these different teams, you want them to work together, all right? And you want to coordinate all these multiple teams for tasks such as, managing the food stalls, stage setup, ticket sales, crowd control, and doing it all alone is not possible, right? It would be impossible to do all of these tasks alone. So you divide the work amongst different teams, all right? You create different teams, each team with specialize in a specific task, all right? And you hire a skilled coordinator who will ensure that all of these teams are together working efficiently, all right? So Apache Spark is like that skilled coordinator that is going to manage this big processing task, all right? And the different teams that we've used here, right? They're like different libraries within Spark, right? That handle specialized tasks, and the events scale, all right? It represents the ability of Spark to scale from running on a single laptop to a cluster of thousands of servers. When you create cluster in Spark, right? When you create cluster of compute, there's no limit on it. You can add as many machines as you want. All right. So the essential understanding from this entire architecture is that to perform a bigger task, you should ideally break it down into smaller achievable units of task, and you should go from there, right? That is the core ideology of Spark. Break the task into smaller pieces, process it on parallel, combine the result, and instead of writing and reading data from disk, use the memory, all right, read and write data in the RAM and process it in the RAM. And with that, you will achieve really high, results, efficient results, quick results. All right. So we'll stop the demo here today. Uh, I wanted to touch upon Databricks as well, because this course is not about Spark or Azure, it's about Databricks, right? But we have limited time. So the free session, it ends today. From tomorrow onwards, we'll have the paid session. You can get in touch with the backend team for any of your queries regarding the sessions. All right.
Hi, sir. I have a question. Like regarding the 1 TB data that you explained, right? Within Hadoop, sorry, within Spark, the driver process will divides the 1 TB of data into multiple chunks, and each chunks will be distributed across different clusters. So
Yes.
once the cluster gets processed, right? I mean,
Mm-hmm.
not the full file is being processed, only a part of the cluster is being done.
Mm-hmm.
You told like that data will be stored, will be stored, but where it will get stored?
In whatever file system you're using. All right. See,
Then again, we will have the same
no, you will not.
IO
See,
latency, right?
no, no, no. So the issue with Hadoop was that it was keeping all the intermediate results in the disk, all the
Yeah,
data,
yeah.
right? While processing the data, also, if you needed to store the data somewhere, right? Let's say after performing one set of transformation, you wanted to store data somewhere. In Hadoop, even that was being stored in the disk, right? And that is what Spark eliminates here. Because eventually, when you start collecting data in the final location, right, there is no need for you to read that data again, right? So once you've processed the final data, let's say you read it from an Azure storage, right, and you want to load all of that data somewhere else, for example, let's say into an on-premise environment or Amazon S3, wherever the storage location is, right? Whether you read it from Azure storage and you want to put it back into Azure storage, let's say, right?
Hmm.
Then in that case also, the processing is not happening on the disk. You're not reading and writing to the disk for the processing task. You can read the data from the disk, and the final output could be written to the disk.
Okay, in my case, the final output is something which involves some aggregations. In that case, aggregations can be happen only when all the data has been processed, right? Each clusters is only processing a chunk of data.
Yes,
So
so for
how that
that we discussed no that there is something called as shuffle. If you need the data again to be read, let's say to perform an aggregation towards the end, or a group by clause to run the group by clause towards the end, then you have something called as a shuffle, which will
yeah,
again.
shuffle will redistribute the data to a same cluster, like say bringing back the same uh, kind of data in a single cluster. But to do that, each data has to be processed before by that individual clusters, right? In between
Yes,
them,
yes.
where does
That
that
happens
data get
in
stored?
memory. That happens in
No, no,
memory,
no.
right?
Data processing happens in memory.
Right.
Say first chunk has processed 5 GB of data.
Okay.
So it says like I am done. So provide me the next set of data of the same file.
Right.
Okay. Where does that 5 GB of data get stored before getting passed to the suppling phase? Because for suppling phase, we need to have that other clusters data also to be processed. And I mean, the other cluster has to complete their process, right? Where does that intermediate results get stored? Whether it sends back to the disk or where it gets stored.
See, so whatever persistent storage you've defined, right? So one is the default processing that happens in the memory. All right. By default, Spark is going to store all the intermediate data in the memory itself, right? In case that there is not enough memory for the intermediate results to be stored in the RAM, all right, Spark will spill the data back to the disk. All right. And this is also managed automatically by Spark. We call it fallback.
Okay.
All right. So Spark will use this technique, which is called as spilling, to write the part, right, or intermediate data back to disk temporarily. All right. Before it can go ahead with complete transformation.
Okay.
This is
So
slower than in-memory processing, but this will ensure that Spark can handle a larger data set, all right, than the available memory. I think that was the gist of your question. If the data itself is bigger than the memory available, correct?
yeah, correct.
Yeah. So
Correct.
it will write back to the disk.
Okay. Okay. So the only advantage, the main advantage which Spark has over Hadoop is
While
the
processing.
memory while processing. Okay.
Yes, yes, yes.
Okay. Okay.
See,
Okay.
because when you are reading and writing the data to the disk, it's only a one-time operation. You read it once, you write it once, correct? From the main
Yeah.
storage. But
Mm.
while processing, there can be certain situations where you have to write and read data multiple times, right? Now that was creating a bottleneck in Hadoop. The main issue was that while processing itself, you were multiple times writing the data to the disk, reading the data from the disk. Whereas with Spark, you're doing it in memory, that speeds up the entire process.
Okay. Okay. Got it.
All right, then, so we are well over the time. Uh, as I said, today we had our free session. Yesterday we had our free sessions. From tomorrow onwards, we'll have the paid sessions. So you can get in touch with the backend team. We'll discuss a lot more. This was just like 2 or 3% or 4% of the entire discussion that we want to do. I would say 2% only, because the main objective of this course is to work on Databricks, right? So I would request everybody to join us on this journey from tomorrow onwards, and we'll start again with the basics of Azure, because I want you to understand what Azure is before we can dive into Azure Databricks, right? If you don't know Azure, right, how would you comprehend Azure Databricks on the whole? So I wanted to, familiarize you with certain services which we are going to use. For example, the data lake, we'll see Databricks' integration with data lake also. So you should know what Azure Data Lake is, how you build it, what are the features. So all of that we'll cover in the basics of Azure. Then we had a brief discussion on Spark today, right? Very brief. We'll go more in depth to understand the Spark architecture and the Spark APIs, the high level APIs and the low level APIs. And we'll try to understand the difference between the two and then how you're going to use them, the high level APIs. We'll generally work with the high level APIs in the form of data frames, right? And then we'll see Spark SQL, various other, we'll see our examples in PySpark also. We'll try to understand PySpark as well, right? How do you perform basic operations with PySpark? We'll see certain examples with Scala also. We'll try to understand how you write Scala programs. And then we'll move towards Databricks, where we have a lot of features to cover, right? So uh, we'll close it here. I expect all of you to join us
So,
from tomorrow
hello,
onwards.
hello,
Yeah.
Sresh. I actually one previous basis student. Sorry, I do not know. I am talking about something else. I think I need the lab again. I think the backend team contact with you. Can you give me the lab again?
Yeah, so we'll be having a couple of projects on Databricks, all right?
No.
Toward
I do the Azure Data Engineer previous course. I
Mhm.
need the lab, the previous lab. I
Yeah, you can contact me offline.
I do
Yes,
not.
Ashik, we will give you this week.
Okay,
Actually,
okay.
I just told you, right, in the
Mhm.
evening.
Oh,
So,
sorry. Okay,
yeah, I
okay.
Yeah, yeah,
Thank
asked
you.
him already. He
Okay,
will give you with the current batch.
okay.
yeah.
Thank you very much. Thank you.
Yeah. So, Shreyas, somebody raised a hand.
I have a quick question. Yes, it was me who raised the
Yeah,
hand.
please.
Yeah.
Just had a quick question. So our organization is considering PySpark cluster and Databricks. There's a lot of back and forth between that. Just wanted to see what your take between both these solutions is, and why Databricks is more favorable and widely used. So just under the hood, I think it's the same concept, but yeah, I wanted to hear from you. Over. Thank you.
So you want to understand why your organization is moving towards PySpark and Databricks? Is that the question?
Uh,
Or how they're
ye-
related?
yeah, how they're related, because we as a team have to make the decision, and I'm trying to gather some information
All right.
around that.
So PySpark is the Python API for Apache Spark. All right. It allows users to write Spark application. You can develop Spark applications using PySpark, all right, or Python, right? It's a Python-based language. So it provides an easy way to work with this large data set and perform processing, right, using the Python syntax, right? Correct. Now, PySpark will leverage a lot of powerful features of the Spark, right? Or the distributed computing capabilities of Spark, and it can perform tasks like ETL, machine learning, real-time streaming, data processing in general, data cleaning. So all of that you can do using PySpark. So PySpark lets you write Spark application. Coming to Databricks, it's a cloud-based data engineering and analytical platform which is built on top of Apache Spark. All right. Since Databricks is built on top of Apache Spark and you need PySpark to interact with Apache Spark, right? That is how you work with PySpark in Databricks as well. Is it understood now?
Yeah. So why should I go for Databricks when I can do the same thing in
You
PySpark?
Because Databricks is going to give you a lot of features. See, PySpark is not a platform.
Mhm.
It's just a language.
Yeah.
Databricks is a platform. It's a tool that can
Mm.
help you do multiple things.
Uh,
PySpark
okay.
is just a part of it.
Mhm.
All right. Databricks is not just only PySpark. All right. It provides you a notebook. Databricks will provide you a notebook interface, which is very similar to Jupyter Notebook, where you can write all your PySpark code. But then
Mhm.
PySpark is not going to manage your cluster or create your cluster. Who's going to create your Spark cluster? Databricks will create the Spark cluster in the backend. All right. And
Okay.
you need Databricks to create that cluster and using PySpark, you're going to interact with that cluster.
Okay, so
So Shreyas,
basically a unified a
Yes,
tool to
it's a
do
unified
everything.
platform. Yes,
Okay,
yes.
okay, got it.
You can think like a database. Databricks is like works like a database for all practical purposes, and it has a lot of features like maintaining the history and whatnot. All right, it has
A lot
time
of
travel.
time traveling. Yes,
Yes,
yes. Time
yeah.
traveling, versioning, a lot of things.
Many,
We'll take a look.
many of the aspects of PySpark maintenance are being handled by the Databricks, and also cluster management and scale up, scale down, and whatnot. All right, and all those are being managed, and also metadata management. Right, all those details are maintained within the Databricks environment,
Databricks environment. Yes.
and yeah, that is one of the reasons.
So going forward in the course, we'll discuss all of this, right? As to how and what are the various features Databricks has to offer. So as I said,
Shreyas,
yeah,
uh,
Thank you.
yeah.
it is like Hadoop, right? It is the next level of Hadoop
It
that
is
will
not
that
nothing to do with Hadoop here. Hadoop is already its legacy. We never normally no one is using the Hadoop. No one, I wouldn't say no one, but most of the places like Hadoop is a kind of legacy. Now everything is done in the cloud based, right?
okay.
Like yeah.
So so
Yeah.
here Databricks will be the platform for us to do
Yes.
anything like
Yes.
so. Yeah.
You're right.
Yeah. So I just wanted to know one thing, like we need to do as Shreyas said, no, just we need to do the backend thing as well. So
Okay.
for backend thing, what platform like
When you say the
uh,
backend, what do you mean with backend? I mean all the data related, right? Activities.
mhm.
Yeah.
So here for backend, can we use Unix or that Linux
You
for hmm?
see that is the operating system you're talking about. So
Okay.
when it comes to Databricks is always a cloud-based, right? You can
Mhm.
have either most of the times people use Azure because Azure and Databricks they
See,
integrate very well.
yes,
Yeah,
absolutely. There is no direct relation with operating system here because uh, operating system is directly not required for Databricks. It's a
yeah,
managed cloud platform. It
right.
runs on the cloud. It does not run on an operating system. All
Yeah,
right.
yeah. There are
And
So
only
if
two
I
concepts there. In fact, one is that platform where we're talking about two things. One is the storage and the other one is compute. Compute storage. These are the two things when we talk in the cloud platform.
yes,
Mainly.
absolutely.
Yeah.
okay, and Shreyas, what will be the fees for this course?
For that, you
Oh,
can contact the backend team.
okay.
Yeah.
Can we have a contact for the so that we can call them or something, or do
Yes,
we need to
yes.
call
Uh,
Chandra sir?
wait. I think I'll ask them to put the details, or they'll share the details with you. They have the WhatsApp number, right?
So, WhatsApp number I have. Yeah,
Yes, yes. You contact it on the
I
WhatsApp
have.
number, and they'll get in touch with you.
Okay, I'm added in that group. Yeah,
Yeah.
and I just wanted to know one thing, that what will be covered, like Databricks, then PySpark, then what will what will the topics covered in this session? Databricks, then
You
PySpark.
want you can ask them. They will share the entire TOC with you. We have a entire TOC.
Okay. So what will be the duration for this course?
The duration would be approximately around 30 working days.
30 working days. Okay.
Yes. So
Okay,
30
okay.
hours. Yeah.
Thank you. Thank you so much, Shreyas.
Yeah.
One last question. I know you mentioned Kubernetes, right? So how does that
Mhm.
come into play in this whole project?
See, when you have a cluster of compute, right, you need cluster managers. So you have Yarn, you have Mesos, and similarly, Kubernetes is also a cluster manager, right? It manages the cluster of compute. So even Kubernetes can be used to manage this cluster of worker nodes.
But
Okay.
So
Uh,
they'll share with you
so
the.
Kubernetes also covered in this cover in this
Not really. We are
session.
not worried
No,
about
no.
cluster managers. We'll use the Spark's standalone cluster manager. We don't need a separate cluster manager. We'll have a brief
Okay.
discussion on what all different cluster managers are there. If there are any
Yes.
benefits that one offers in comparison to the other.
So from tomorrow onwards, it will be paid
Yes.
or
Tomorrow onwards, it will be the paid session.
okay, paid session. Okay. Okay. Yeah.
All right then.
Thank you. Thank you so much,
Thank
Shreyas.
you. Thank you everyone for joining in. I wish to see all of you tomorrow. Thanks a lot, guys, for being a part of this session.
Thank you.
Thank you.
Shreyas, one thing, practically, it will cover practically as well, right?
Yes, yes, we'll give you hands-on as well.
Okay, thank you. Thank you so much.
Thank you all.